Continuing on the same theme, so we have two alternatives. Our liquid, mostly water, but our liquid is on the surface of a rough surface, and it's either bridging across, so not going into the gaps, or it's going into the gaps. And that generates two possibilities where the contact angle is increased or is magnified by the surface area increase, and that can be either upwards if it starts off bigger than 90 degrees, or downwards if it starts off less than 90 degrees, because it goes via the cosine function. So mathematically it goes via the cosine function, and the cosine function passes through 0 at 90. So when it's less than 90 it becomes more and more negative, and when it's more than 90 it becomes more and more positive. Physically what it means is if the surface is attractive to the liquid and you make it rough, it makes it more attractive, and if it's unattractive to the liquid, it makes it more unattractive. In chemistry terms, it's always attracting, but the liquid can attract itself stronger than the solid attracts the liquid. So that it depends on the balance of forces and not on the absolute force. The demonstration of that is if we take a piece of Teflon, which is really, really water-hating, hydrophobic, and we put it onto water, a water drop will stick because there is still a positive interaction there, it's just smaller. If we go to this case, which is the Cassie and Baxter case, then we're skating across the top, and we get an angle which is dependent on the fraction of the surface area that's solid, and the fraction that is gapped, that is bridged. This is originally, or can be thought of, as being a mixed surface. So if we took a surface that was made out of Teflon and glass in some kind of pattern, then we could use the same equation. In both cases, we have to make some assumptions to be able to use these types of equations, and that's critically important. It's critically important with every theory that we use in physics, or in chemistry, or in biology. So we must know what assumptions we've made. In this case, to make the force assumption that the force is the average of these, the force has to actually be the average of those, and that means that at the edge of the drop, it has to sample some of each of these, the equivalent proportion, which means if our surface is a series of lines in one direction, it won't work. The angle will appear to be different on one direction than it is on the other direction. If we have roughness, where it's wetting in, we have the same effect. That if it's not the same in every direction, then we will generate some kind of directionality. Likewise, if we make our pattern, for example, very, very big, at some point the water, the surface tension, will not be able to bend to get from one to the other, and so it will appear to not be rough at all. If we take a hole in the ground that's a meter wide, it doesn't behave like roughness to water. It's just a hole. If we go in the opposite extreme and we shrink it and shrink it and shrink it, at some point water molecules can't go down at all, and then it doesn't behave like its surface at all. So there is a size range where it behaves properly, where it behaves like it's a continuum, and where it can skate across if it wants to, where it can fill it if it wants to, and there are size ranges where it may not work. Continuing on the theme, if we then try to slide a drop over that, we see exactly the same effect, that if we have made it rough and it's penetrating into the roughness, a Wenzel type roughness, then the hysteresis, the difference between the front and the back edge of the drop, or the difference between when we're increasing the volume and decreasing it, is greater. It's got more surface area to interact with, and also the water or liquid can get trapped down these holes and pulled back. It can't get trapped in one it's not in. The Kelsen-Baxter skating version is special because now we're touching less surface. And if we're touching less surface, it can't stick to the bits that it's not touching. So it can only stick to the bits it's touching, and that makes it have less hysteresis, makes it less difficult to tip off our surface, and in extreme cases it rolls off. If we also make that anisotropic, we make it in a direction, so we have grooves in one direction, then it's, for some cases, easier to move along the grooves, and in other cases it's more difficult. So if we've got Wenzel grooves, they're wetted, then it's difficult to tip it out of the groove. If we've got Cassian-Baxter grooves, they're not wetted, and it's also difficult to tip it out of the grooves because it would have to get to the next pillar. If it's Cassian-Baxter grooves, then it should be easier for it to jump across, as it's the normal Cassian-Baxter case, then it should be to move along, because then it's doing exactly the same thing as it is doing normally along the lines of the surface, although in that case there is less surface, so it's still going to be less hysteresis than it would be on a flat surface. This effect, or these effects, are deliberately used by plants, so not really deliberately because it's evolution that's doing it, but also by us deliberately. So what we can do is we can generate a set of surface that's very hydrophobic, that's got pillars on it that have a cushion of air underneath. So if we put a drop on it, it will be very mobile. We can generate a surface that is very sticky, and we can make our liquid go to there. If we want to print something that's finer than a drop could possibly be, so if we want to print, for example, a DNA test with pattern of DNA, and we want the drops to be smaller than a drop would be if it's spread on the surface, we can make the surface very hydrophobic, so the drops draw up, but have little patches that are hydrophilic so that it will stay where we want them to be rather than where they roll to. The problem with making it very water repellent in this fashion is that the hysteresis is low, so if we print a drop of liquid onto it, it will roll around and go somewhere where we don't want it to be. So we can pattern the surface to do so. Plants that do this typically have a superhydrophobic leaf, but they have a region that is either superhydrophilic, it's Wenzel wetting, but low contact angle, so it goes to 0, and then when a drop of rain comes along, it bounces off the leaf. But if it bounces off parts of the leaf and sticks to the center, then it will run down the stem and water the plant. This is particularly observable in rockery type plants, where they're expecting there to not be very much water, and that water that doesn't go directly to their roots is not necessarily useful to them. If we plot the Wenzel equation, which is when it's wetting completely, which was on the bottom on my last picture on the board, and we plot it against the contact angle on a flat surface, on a smooth surface, against on a rough surface for different contact angles, there is only one point where nothing happens, that's 90 degrees, because there's no interaction. The interaction with the surface is exactly the same strength as the interaction with the water itself, which is why you get half a circle, half a sphere on a flat surface. If you make it rough, you also get half a sphere, so that's that point in the middle. As we increase the contact angle above 90 degrees, the contact angle on a rough surface goes up very, very rapidly, and you can see that curve. Let me put above here, it's a sort of blue color, and it's a slightly S-shaped curve going off to infinity in both directions, because as I mentioned when we were talking about it, it soon breaks the equation, it soon passes 180 degrees or 0 degrees, and we can't compute it, so something weird happens. The Cassian-Baxter equation, where it's skating across, where it's suspended on higher contact angles, higher than 90 degrees, is really easy to imagine that it's just repelling it more and more. But if we consider that it could be suspended on a hydrophilic surface as well, we might have to do some tricks to make it do that, then if it is, we can consider it to be this red curve here. So that's mathematically what we would predict if it's physically possible to do it, which it is, but it's not always easy. What we really see very often is the combination of the two curves, so the lower one, whichever it is, whichever one is lower, it falls on that one. So if we follow the blue curve up from the bottom here, it would go along the bottom, up the curve, and then along the Cassian-Baxter curve, which we can see in this experimental one here. So this is me taking different liquids, because the different liquids have a different contact angle on the same surface. Then I don't have to make, I didn't have to, because it was me doing the practical. I didn't have to make lots and lots of surfaces. I'd use the same one. If you take different liquids with different surface tension, different contact angles on the same surface, then you can see that it follows what I just predicted. It goes 0, 0, 0, 0 because we had not compute, and then it comes off the baseline where the Cassian-Baxter formula approximately says it should, and then it goes up very, very readily until it gets to a very high value, and then it doesn't go up very much after that. It was difficult to get lots of points on this curve, so it's not ideal, but you can see how it relates to the other one. What's interesting is that we can see that there is a kind of transition. So if we look at the glycerol and the water, the glycerol sometimes you can balance it on the top and sometimes it sinks inside. Water always sits on the top unless you force it. And mercury is pretty much bound to go to the top. Even if you push it down, it jumps back out again. The ones on the bottom, it spreads completely inside the surface, and they see no contact angle. The good thing about this is that we've resolved the problem with the Cassian-Baxter equation going past 180 degrees, because it just jumps over, it just doesn't bother to go to the wetness and into the roughness, and that gives us a lower contact angle. So we don't have to imagine that it levitates off the surface or something weird. And on the zero end, we can think about what it might do. We can think of something called capillary action, where the liquid is drawn between the surface. So if we consider the classical variation, we would take some toilet paper and we would dip it into water, and the water is drawn up it against gravity. Exactly this is happening horizontally, so it's drawing the liquid away, and that makes the drop spread faster than it would otherwise spread. This is an aside. I wanted to get to the speed of spreading, but this one is an aside because it's showing us the dotted lines in the middle, where this was an experiment again that I did, where you can get both contact angles for a range of surfaces, depending on how roughly you apply the drop. It either balances on the top or it goes in. The rule of which one it does is not quite so easy to determine. So if we do the experiment with a drop spreading on a surface, we can see that on a flat surface we get the top curve where it spreads, and it slows down as the angle gets smaller and smaller and smaller, because there's more and more resistance in the viscosity as the thickness gets smaller and smaller. So it takes a very long time to spread properly. If we do it on a rough surface, we discover that it continues spreading for longer, because it's not really spreading across a flat surface, it's being drawn in. And in our case, we had a pattern, so those funny zigzags, the funny dips in the plot, come from it spreading across pillars. That gives us an exponent, it gives us an equation, there's an old equation for it, that tells us that it should spread with a certain exponent, with a certain power, and now our power is higher, so it slows down less fast with time than a drop on a flat surface. So it is possible mathematically to see whether we have got super spreading or not. Practically we can't see it with a drop because it always goes to zero contact angle, but it is possible by measuring the rate of change of speed.